Hello, I'm going to talk about climate change and its effects on the world. I'm going to start by showing you how rapidly climate is now changing, and then talk about how we might be able to do something about the impacts that climate change is having on our planet. So we can start by looking at this graph, which is only recently been developed. We now know how to be able to measure the average temperature of the Earth way back to about 1 million years ago. This is mainly because we're using the record from ice cores. That's cores taken through the Greenland and Antarctic ice sheets. So by some careful calculations with this, we're able to measure what the temperature of the Earth was like over the last 1 million years. And also, by taking very small samples out of this ice core record, we can get at the tiny bubbles which were inserted in the ice when the snow fell that produced the ice sheet. And by taking out the carbon dioxide from those little bubbles, we can work out what the carbon dioxide content was on the planet over the last 1 million years. Now, carbon dioxide is the most active greenhouse gas, the most important gas causing global warming. So it's now almost miraculous that we can say how much of this carbon dioxide there was in the atmosphere back over 1 million years. So here we see it, and what we can see is a kind of sawtooth pattern. If we look on the right-hand side here, we see that the carbon dioxide level in the atmosphere was about 280 parts per million during the warm periods. That's when the CO2 level was high, and then it dropped down slowly to a minimum of 180, and then it rose very rapidly, and that brings us up to the present day, or to 1950, because there's been a radical change in the amount of carbon dioxide in the atmosphere during the last few years, the industrial period. So if we look now at the right-hand side of the graph, we see the previous ice age, which is that low level. It rises quickly to 280. That is, the ice melted, brought us up to what's called an interglacial. That's what we're in at the moment, a warm period. And then it cooled off, and the ice came back again to the last ice age, and then it rose rapidly again to the present day. It rises quickly and drops slowly because when the cause of the ice ages, which is a wobble on the Earth's axis, that causes the ice sheets of the world to grow, but they can only grow at a certain rate, which is the rate at which snow falls on them. But when the wobble changes again and the Earth is trying to warm up, the ice and snow melt more quickly, because you can melt as much as ice as you can supply heat for, whereas when you're freezing, you can only freeze at the level at which the snow falls. So we have a kind of sawtooth pattern. We emerged from it rapidly, and that's the last few thousand years. And then the carbon dioxide level rose to this level of 280, which seems to be the level that the Earth would like to have in between glacial periods when it's warm. And so we rose to that in 1950, and then we rose much faster to an even higher level, which is the one we show here, which is over 400 parts per million. This is what is the chief cause of accelerating global warming today. Well, let's look first at what that's done to the amount of sea ice in the world. Now, we know that one of the big effects of warming is going to be ice and snow are going to melt. That will happen far faster than any change in landscapes or any change in rocks. In fact, as the current saying says, you can't argue with the melting point of ice. That's the first thing to go when the climate warms up, is ice and snow. So here we see what the situation was in the Arctic with sea ice, that's the blue substance here, what it was in the 1970s, which is when I started to do work in the Arctic. And we see that in the summer, on the left-hand side, the sea ice retreats a little bit from the coastlines of Siberia and North America, but only a little bit, not usually enough for a ship to get through very easily. Then in the winter, on the right-hand side, the sea ice grows, fills the whole Arctic basin, also fills Baffin Bay, Hudson's Bay, and part of the Bering Sea, and part of the Sea of Okhotsk, all the way down to the Japanese coast. This was the standard cycle of winter versus summer in the Arctic. But on top of that was a trend which at first you couldn't really see. And this trend started, we think, in about 1900. And this graph shows how the seasonal ice cover in the Arctic changed. And we can see that the brown curve, which is the bottom one, the ice, that's the summer ice, disappeared more quickly than at other seasons of the year. So from 1900 onwards, the summer ice was retreating fast, but the ice in other seasons was retreating slowly, and people didn't really realize that the Arctic was changing. But when it changes through a large enough amount, we do realize it. And this is the difference between the way the ice was in the 1970s and the way the ice is today. On the left-hand side, the yellow line marks the summer ice limit in the 1970s, while the blue shows where the ice limit is now. So about half of the ice, or more than half, of the ice area in the Arctic that existed in the 1970s no longer exists in summer. In fact, you can very easily sail a ship through the Northern Sea Route or the Northwest Passage to get from the Atlantic to the Pacific, which you never used to be able to do. The right-hand side shows a rather smaller effect, which again is a retreat from the yellow, which was the winter ice limits in the 1970s, to the white, which is the winter ice limits today. There's still a lot of ice remaining in the winter. So that's the ice effect. But if we look at the temperature effect, we saw this big sawtooth pattern over the last million years. But when we look at the last 1,000 years, which we are again able to do from ice cores and other methods, we see, that's in the bottom graph here, that the average temperature of the Earth stayed very constant, or relatively constant, right from the period when this graph starts. That's the year 1000, when the Vikings were in Greenland. And there was a very gradual decrease, which means we're heading towards another ice age, but heading very slowly. And that lasted until about 1850, and then suddenly the temperature took off upwards. Clearly a different process is going on than was happening during the first 1,000 years of slow change. And that shooting upwards is entirely a product of the Industrial Revolution, when we started to burn coal, and burning coal produces carbon dioxide. The carbon dioxide increases the temperature of the air. This is something that people didn't initially realize was happening, but it certainly is happening. And if we expand the bottom curve and look at just the last 100 years, we see how the temperature has risen, and the there was a pause in about the 1920s, 1930s, and then it's carried on rising rapidly since then. There was no explanation for this when we first started measuring air temperatures in the 19th century. They were rising because we were burning coal and then oil, but nobody could measure that they were rising because we didn't have meteorological offices in the world. Nobody was routinely measuring air temperature. So the temperature was rising, we didn't know it. The first scientists to really show that the temperature should be rising with all this carbon dioxide going into the air was a Swedish scientist called Svante Arrhenius. And this is the famous paper that he wrote in 1896, which explained the warming of the atmosphere as being due to increased amounts of carbon dioxide being put into the atmosphere by man. And why does this happen? Well, this is a very brief explanation of why the greenhouse effect happens. The right-hand curve here shows the amount of energy being radiated back from the Earth back to the Sun. There's a balance of energy between shortwave radiation, which the Sun is emitting, that reaches the Earth, and that radiation warms the Earth, and the Earth then radiates at longer frequencies, longer periods, radiates energy back to the Sun. So the balance between the radiation from the Sun and our earthly radiation back towards the Sun is a balance which determines the temperature of the Earth. Now, when we look at that radiation balance as a function of wavelength, we see that there should be a smooth change. There's one of the laws, one of the gas laws, that's the Stefan Boltzmann law of radiation, shows that the radiation that the Earth emits as a function of its temperature should smoothly vary with frequency. But when we look at the radiation, in this case it's measured from a satellite above the Mediterranean, we see that there isn't necessarily a simple trend. Instead, we have these big dips, these holes in the radiation distribution, which is due to the fact that some of the radiation coming from the Earth is absorbed in the atmosphere and doesn't get back out towards the Sun. And the bands where this happens, the most important ones are related to the presence of gases in the atmosphere. And the biggest gap here is due to carbon dioxide. There's another one here due to ozone, and another one over here due to water vapor. But you can see that what reduces the amount of radiation going out from the Earth to the Sun, the biggest factor is that carbon dioxide in the atmosphere is absorbing some of it. So a lot less is getting out. And there are other smaller factors, ozone and water vapor and methane over here. So these gases which cause radiation from the Earth to remain within the atmosphere rather than going out back to the Sun, these are called greenhouse gases. The most important is carbon dioxide and methane, ozone, nitrous oxide, water vapor. These are less important. So we'll be talking a lot about carbon dioxide and a bit less about methane during these lectures. That's the gas content. But when we look at the effect of that carbon dioxide, we see that that's the main cause of the increased warming rate of the planet during this century. This is a blow-up which shows how much heating has occurred during the last century or so due to us burning increased amounts of coal and then oil. And we can see that the warming has accelerated and the temperature now is warmer than ever before. The temperature and the carbon dioxide content go together because the carbon dioxide, as we put it into the atmosphere, it absorbs outgoing radiation, prevents that radiation from getting out of the planet's atmosphere, so the atmosphere warms up. So carbon dioxide content and air temperature go together. But the temperature warming is not distributed equally over the whole planet, and this is important for the impacts of climate change on the frozen parts of the planet, because the Arctic warms up much more rapidly than any other part of the planet. This shows the average temperature of the Earth and the change that's happened since the 19th century, but as a function of latitude. And we can see that if we take the global average warming, we can see that in the Arctic, north of 60 degrees, it's warmed far more rapidly than anywhere else in the low latitudes or in the Antarctic. So this Arctic warming or Arctic amplification is an effect which we don't fully understand, but it is such that the Arctic is warming about 3 times as fast as lower latitudes. It really is melting very, very fast. Now we can see that not only does it warm faster, but on the rare occasions when the Earth cools down for a little while, it cools faster as well. So changes in temperature are happening faster in the Arctic than anywhere else. Here we see a period between 1890 and 2010, when for a while the air temperature over the world on average went down. There was a little bit of cooling, just happened for a short period. But when we look at the temperature in the Arctic, not only does it increase more rapidly than the rest of the world, here and here, but when the rest of the world is cooling, it cools more rapidly. So changes in the Arctic, both warming and cooling, happen more rapidly than in the rest of the world. Now, how do we know all this? Now, we know about the carbon dioxide, as I said at the beginning, by using tiny syringes, just like you use for vaccination, to extract little bubbles of gas from ice cores and work out how much carbon dioxide there is in the gas. But for temperature, the best source is measurements made on the top of a mountain in Hawaii. They also measure the present state of carbon dioxide as well. And that's a volcano called Mauna Loa. And it's extraordinary because until 1896, we didn't know that we were putting climatically active gases into the atmosphere. Then we did, because of the work of Arrhenius, but we still didn't bother to measure the temperature or the carbon dioxide content. And that didn't start until 1958 with this observatory that was put on the top of this volcano by the Scripps Institution of Oceanography in San Diego. So every day since 1958, this observatory has been measuring carbon dioxide content of the atmosphere, air temperature, and a lot of other parameters. So we depend on Mauna Loa for our present knowledge of what's happening in the world. And here's the record since 1958, and it's very important because it shows a relentless, accelerating increase in carbon dioxide content, which means, in the same way, a relentlessly accelerating level of temperature. Here we see the carbon dioxide content. The wiggles are because the carbon dioxide content varies seasonally, depending on whether it's winter or summer. But we see that the record started at a level of only 310 parts per million in 1958. Now, 280 was the level at the end of the last ice age. So everything we'd done in the 19th century, all the coal we burned, and in the early 20th century, only managed to increase carbon dioxide content by 30 parts per million, from 280 to 310. But since then, the rate of increase has accelerated. So we see now an accelerating growth, which has gone beyond 400. And these are measurements that I took yesterday, or wrote down from Mauna Loa yesterday. And on January the 24th, it was 419, which means it's up here. And exactly a year ago, it was 416. So the carbon dioxide level is increasing now at about 3 parts per million per year. So in the whole century since we started burning oil and coal, the level only went up about 30, from 280 to 310, but now it's going up at 3 per year, far more rapidly and accelerating all the time. So this is a real cause for worry. This is what we should be worrying about now, the fact that this carbon dioxide curve is accelerating upwards. And nothing we can do seems to be able to slow it down. This red line is the carbon dioxide curve, and all the little markers you have along this line indicate annual conferences about climate held by the United Nations, and these are called the COP meetings, COP, Committee of the Parties. And we see that the level of carbon dioxide continues to rise accelerated way, despite the fact that at each one of these meetings, the world has agreed that something should be done about reducing carbon dioxide emissions. And the big agreement was the Paris Climate Agreement of 2015, which is here. Here there was an earlier climate agreement and an even earlier one. So these are global climate agreements about reducing carbon dioxide levels. But we see that it doesn't matter whether you have an agreement or not. There's no change in the rate of warming. The rate of warming, the rate of increase of CO2 just continues to rise. And the Paris Climate Agreement doesn't seem to have had any impact at all. Here it is, that's 2015, this is now. And we see the rate of rise of CO2 has continued. And it will continue in the future, because if we model the fact that we're continuing to emit carbon dioxide from burning fossil fuels, then the level will increase, and that will increase warming. So here we see a set of curves showing how much the carbon dioxide will increase if we don't do anything about reducing our emissions, which is this rapid rate of increase. And if we do something about emissions, we can keep the rate of increase low. In fact, keep the carbon dioxide not increasing at all. But here we are over here now with quite a rapid increase. So we know that if we continue to fail to do something about carbon dioxide, the rate of increase will keep rising. And that translates into a temperature rise of maybe 3, 4, or 5 degrees by the end of this century. That's something which we can't tolerate. The Paris Climate Agreement of 2015, the nations of the world agreed that they would reduce their emissions of carbon dioxide to the point where the maximum amount of warming by the end of the century would only be 2 degrees. We calculated that 2 degrees is about all that the world can stand without having disastrous effects on crops, on brush fires, on the planet generally. And not only is 2 degrees serious, 1.5 degrees is something that's better. If we can keep to 1.5, it will be even better. But we can see that we're nearly at 1.5 now. And if we keep on increasing our CO2 emissions, we'll get way beyond 1.5 and into temperatures that are really serious for survivability of man on this planet. Let's look at what it's done already. We know, for instance, that the last 6 years are the hottest years ever recorded for the planet, the average annual temperature of the planet. All these previous rises are showing a rise since the beginning of the 20th century. That's when we started burning fossil fuels. The temperature's been rising, and now these last 6 years are the largest amount of rise ever. And we see that the average temperature is 1.25 degrees above the temperature at the start of the 20th century. Now that climate scientists say, well, we haven't reached the 1.5 level yet, which is dangerous. We've reached 1.25. But in reality, we should be starting to count our temperature rise from when we first started to burn coal back in the 19th century. And if we add on the rise that happened in the 19th century to this rise that happens in the 20th century, we do really reach 1.5. So climate scientists are trying to really not to pull the wool over people's eyes, but to minimize the effect. And by saying that the rise is only 1.25, it's really not true. It's really already 1.5 since the beginning of the industrial age. Now, a very clever way of looking at how the planet has warmed over the last 50 years has been to rank the temperatures in each month of the year according to which year was the hottest, which was the second hottest, which was the third hottest. So in this case, we've got a number on each month of the year from January on. We have a number which is the rank that year had. And the blue usually is cold and the red is hot. So here we see that the hottest January were very recently, 1, 2 and 3 are the very recent years were the hottest, and the older years were colder, like number 40. The 40th year is way back here. So we see generally blue on the left, which are colder, and red on the right. So this is ranking the month. And we can go through the whole year here, every month of the year. We can see which year had the hottest, say which year had the hottest October. Again, it was recent years, 1, 2 and 3 over here. And which Octobers were the coldest. It's way back in the 1970s. So you put that together and you look at the colours and you see red is on the right, blue is on the left. That is to say the hottest years are the recent years, the coldest years are the older ones. So this is just for the last 40 years, and we can see that even over that period, the Earth has grown radically warmer. Now, let's look at now, and since things are happening at an accelerating rate, if we look at this year, or last year, 2021, we had a measurement which was the hottest temperature measurement ever made on the planet. And it happened in the United Arab Emirates at a place called Sfide, and it was 51.8 degrees. That's the highest reliably measured air temperature ever. And it happened in 2021. But surprisingly, obviously in the Arabian desert, you expect it to be hot. But it was very hot last year in places that you don't expect. And the most unexpected was a town called Lytton, right up in the Rocky Mountains of British Columbia, which are usually snow-capped mountains. And I've been through Lytton many years ago. It's a small town, high up in the mountains. You don't expect it ever to get very hot, but in fact it reached a temperature of 47.9 degrees, and that was so hot that in fact the town caught fire. The trees that it was embedded in caught fire, and the entire town was burnt down by a brush fire that was due to the very high temperature. So this was extraordinary for Canada, the hottest temperature ever reached in Canada, hot enough to destroy a town. Now, the warming has been most rapid, as I showed, in the high latitudes in the Arctic. And here we see that again from a temperature record from Siberia. And we see that on the right-hand side, the red is showing that Siberia has been warming more rapidly than the rest of the world. In fact, in this region, there was a warming of 6 degrees, which is extraordinary. And what that did was to set fire to Siberia. The Siberian forest and taiga caught fire spontaneously, and some of it has been burning continuously for more than a year. And again, we don't expect that because Siberia is cold normally, it's wet, it's not a place which catches fire. But in this case, it did catch fire, and the Siberian fires have been burning continuously because it's so remote that nobody can get in there to try to put the fires out. So the biggest fire and the most widespread fire in the world is the big fire in Siberia, which is still going on. Here's another fire in a more accessible area in Pasadena, and this was one that I encountered as I was driving by, and here's this. I took this picture in August of 2019. The brush fire in a canyon caught fire and set fire to really the city. And Pasadena is a city. You don't expect a city to burn, but it did. And here it is. For several days, the freeway, which I was on, was closed, and we couldn't go anywhere until the fire had been put out. So that's showing the effect in causing fires. Another effect is that the sea ice has been, as I showed already, has been disappearing, but it doesn't just disappear in winter, in summer rather, it disappears all the way through the year. And here we have several years of record of Arctic ice extent during the spring and summer and then the autumn, so the summer months. And these values have been year-on-year values, but last year was the lowest it's ever been. That's this red line, and it's the lowest right through the year. It's not just that it's a very low value in the middle of summer, it's been a very low value all through the year. So that's what's happening now, that the sea ice is weakening throughout the year, even though the change is most obvious in summer. This is carrying on that curve into this year, and showing that again the recovery from the summer has been weaker, and the blue shows the present state of the ice, and there's a smaller area than there was at the same time last year. The world record so far loss has been in 2012, and this shows the white shows the ice limits in 2012, and the yellow is the ice limits back in the 1970s when there was more ice around. So we see the ice shrinking in summer and winter, and at some point it will disappear in the summer, first of all. Now, what are the effects of that? Well, we can see if we look at particular little bits of the Arctic, we can see changes. Now, this is an interesting part of the Arctic. It's northwest Greenland, and this is when I went with Inuit hunters who were hunting polar bears with dog sledges. So we were on a sledge with the dogs in front of us, and there's another sledge in the distance, and an iceberg in the background. But the flat white surface is sea ice, and the sea ice was thick enough for the Eskimos to hunt successfully using their heavy dog sledges. That's the way it was. That was back in about 2010. But when a colleague of mine went back last year, this is what he found. This is exactly the same location. In fact, it's exactly the same dog sledge and exactly the same dogs. So it's the same hunter going out to show how he hunts polar bears. But instead of being able to walk over thick ice, they were wading through water. And this thick layer of water lying on top of the ice is because the ice is melting, even in the winter. This is March. And very dangerous to have the ice doing this. It's not safe to run over that with a sledge because you don't know how thick the ice is. So that's a change just over a few years in winter. And northwest Greenland is the coldest part of Greenland. And this means we can't do things anymore that we used to do in the Arctic. One of the ways we study ice is to go out in the winter, set up a bunch of huts to form an ice camp, and have equipment in the huts to do observational measurements of the ice and the air and the water. So here's the place where each of these 6 people lived in each of these huts, and I was one of them. This was the mess where we ate and cooked. This was the generator hut for electricity, and this was the science hut where we did all our measurements. So this was maintained by plane and by helicopter, and you went there for 2 or 3 months in the winter, and then you came away. In fact, you generally demolished these huts, but you can't go there anymore because this solid ice called multi-year ice, which is more than a year old, which gives you a thick ice surface that's safe to work on, is no longer there. It doesn't exist anymore. And so it's unsafe to work on Arctic ice in the winter, which is makes it difficult for scientists. So what we have to do now is to freeze a ship into the ice like this, and then work from the ship so that if the ice breaks up because of warming, we don't fall through the ice. We're safely on a ship. So the measurement of how this ice thinning has happened, it's quite a difficult thing to do. You can use your satellite to tell you the area of ice, but to measure the thickness, you have to go underneath the ice and look upwards from below. So for that, you have to use a submarine, and we've been making use of Navy submarines, British Navy submarines and US Navy submarines, to go under the ice and to look upwards with an echo sounder. So this shows what it looks like to see the submarine surfacing through ice. They put us ashore so we could do that filming. Here it is emerging from the ice. and this is how we lived. It was me and a colleague doing the measurements from below, but a submarine is a military vessel. You don't have comfortable cabins, and we had to sleep here in a rack where they normally store torpedoes. Very, very uncomfortable. And the submarine also is very, very cramped. There's equipment everywhere, and this is what it's like in the control room where the submarine is controlled. Now this was the last voyage we did, and in this case we had an advanced form of echo sounder, which doesn't just give you a record of the reflections from the surface, but it gives you a proper record of the three-dimensional shape of the underside of the ice. So you mount that sonar in the top of the submarine here, and it shows you ridges in the ice, which are called pressure ridges, and here we see some of them with the ice piled up underneath. This is the older kind of measurement where you're just using a single echo sounder looking upwards, which is telling you how thick the ice is, giving you a reflection from the bottom. And we see that the ice was a mixture of thick ice, this is called multi-year ice, thinner ice, which is refrozen leads, and first-year ice, and these ridges, which are caused by the wind piling the ice up underneath to form these ridges, which can be 40 or 50 meters deep. Now, this is what the multi-year ice and ridges look like. This is what the whole Arctic looked like when I used to work there in the 1970s. But when I work there now, it's not nearly as impressive. The ice doesn't last many years, it just lasts 1 year. It's called first-year ice. It forms and then it melts. And it's very thin, as you can see. Sometimes you would fall through ice like this. So it's a completely different landscape for the Arctic than when there used to be. Big change from that to that. And that change is a change in the thickness of the ice and a change in the area. And when we combine the two, we see that the volume of the ice, that's the thickness times the area, is decreasing very, very fast. And we can see since 1970s, it's decreased to a quarter of what it was in 1979. So this is, the red line is the present volume of ice in the summer in the Arctic, and this is what it used to be. So we see a very rapid fall off of the area and thickness of ice. Well, what are we going to do about it? This is the frightening thing. The main thing is that the amount of carbon dioxide we're emitting is increasing all the time. Now, some countries are doing something about reducing their emissions. This shows the emissions from Europe, that's the blue, and the USA, which they're both showing some recent decreases. But those are more than offset by big increases in the emissions from China and India. And the reason for this, of course, is that industry in China has grown very rapidly, and we are now getting Chinese factories to make the things that we used to make ourselves in our own factories in Europe and America. So the European emissions are going down a bit, but the Chinese and Indian emissions are going up fast. You combine the two and we can see that global emissions are continuing to increase. And as I showed in that earlier graph, we have no sign that the global emissions are decreasing. And the first graph showed carbon dioxide, and now we can see that methane is also increasing rapidly, and it started to increase in the year about 1850 to 1900, with the Industrial Revolution, again because of burning coal. and it's been shooting up. And so methane and carbon dioxide are both actively contributing to the greenhouse effect. Methane seemed to come, this is some methane measurements made in the Arctic, and methane seemed to be reaching a level. It looked as if it wasn't rising anymore, and these fluctuations are just the season change. But then it started to take off again. And we see these little blobs around, and these are single blobs of methane, which we think are coming from emitters in the seabed, in the Arctic seabed. And I'll show that now. And the result of that has been that carbon dioxide has been increasing steadily and accelerating, as I showed, but methane went rapidly upwards, flattened off in the first decade of this century, but has then taken off again and is increasing even faster. So methane is growing even faster than carbon dioxide. So we start to look at what are the consequences to climate warming of this increase in CO2. The first, of course, is warming of the atmosphere. The next one is that this causes a sea level rise, which is very, very important for the planet. That is to say, global sea level is now determined by the amount of ice held in the Arctic and the Antarctic on the Greenland ice sheet and the Antarctic ice sheet. As the temperature warms up, that ice starts to melt, and the melting of that ice causes global sea levels to rise. Now we see that sea levels were rising slowly right through the 20th century, but now they've taken off, and the predictions caused by us continuing to emit greenhouse gases which are causing the ice sheets to melt are that the global sea level is going to grow in an accelerated way, and we might, from these observations and predictions, have a sea level rise of just over 1 metre by the end of this century. But as time has gone on and people have done more measurements, these measurements have got higher and higher. So the estimate of what sea level will reach by the end of this century is now gone beyond 1 metre and is gone towards 2 or 3 metres. And we can see that this loss of ice if you climb around on the Greenland ice sheet and look at it. So I was up on the Greenland ice sheet in August, the middle of summer in 2019, and this is what I saw. Firstly, there's no sign of any snow on top of the ice anymore. That's all melted away. The air temperature, which normally stays below 0 all through the year, was up to 21 degrees, enormously warm. And on that day, 12.5 billion tonnes of ice melted off the Greenland ice sheet. Incredible. And when you look at the ice sheet, you find that the result of the ice melting off is that a lot of dirt that was deposited on the ice sheet in previous decades or centuries is now exposed because the ice has turned into water and run away, and you're left with the dirt. And so this is called black ice. And the problem is the black ice causes even greater warming because the black ice is a bigger absorber of heat than white ice. So this black ice surface on Greenland is causing Greenland to warm even faster. And here we see black ice covering the white ice, which was the clean ice that used to be there. And we see what that's doing to sea levels. That sea level of the world is rising steadily, and it's going to be reaching levels that will cause flooding of many parts of the world, including Venice. So this global warming effect, the first impact is this increase in sea levels throughout the world. So let's look at the next effect, the sea level effect. We already see going on. When you have Acqua Alta in Venice, it's because not only is it a high tide, but it's the fact that the water in the Mediterranean stands at a higher level now. We're getting increasing amount of flooding in coastal cities, and that will get worse and worse as sea level continues to rise. The second effect is a one that I'm personally working on and very worried about, which is a methane impact. Methane, we've already shown, is one of the greenhouse gases, which is not as important as carbon dioxide, but quite important. And we've found that one of the main sources of methane now is the ocean. And this is something that worries us a lot, because if we look at the Arctic Ocean, here's a bathymetric map of the Arctic Ocean, it shows that the center of the Arctic Ocean, because it's an ocean, is very deep, 4,000 meters, that's the dark blue. But the Arctic Ocean has very wide continental shelves around the edges, that's the light blue. And these continental shelves are only about 100 meters deep, 50 to 100 meters deep. Now that's a real source of danger, because at the bottom of the Arctic Ocean, there is a very thick layer of sediment, which is made up of this stuff, which looks like ice, but actually it's methane gas dissolved in ice to produce a substance called methane hydrates. So it's sitting there as a solid material, but full of gas. If you put a match to this, it will burn. And I'll show you that later. It looks like ice which burns. But this methane gas is a really dangerous material, and it's at the moment trapped underneath the Arctic Ocean in these sediments. But as the sediments start to thaw out, and the temperature of the seabed goes up because the sea ice has disappeared, then this methane will come out of the sediments and will come up to the surface as a gas. And that's happening already. So here we see what would happen. The methane is trapped in the form of under the sediments. The sediments melt, this thaw out, and the methane escapes, comes up to the surface. And when it reaches the surface, it's turned into a gas. So it's very dangerous. You can set light to it. Here's a hole in the sea ice. You put a light to it, and it causes the methane to burn. And here's some sonar measurements, very impressive, of methane plumes. This is the seabed, about 50 meters, 60 meters down. This is the sea surface, and these are plumes of methane coming out of the seabed, rising to the surface, coming out into the atmosphere. And these plumes reflect sound waves. So this is a sonar system that measures sound waves reflected by the rising methane plumes. So this is an area 3 or 4 kilometers across, which is full of methane coming up from the seabed, rising to the surface. And if you try and set light to it, you'll get an explosion perhaps at the water surface. Here's another sonar picture of the same thing. You can see the water depth is only 70 meters. The methane comes up, it comes out of the water surface into the atmosphere. And here are methane plumes. And this is what it looks like if you actually look at it from a diver's point of view. These are the methane plumes rising in the form of individual bubbles. In this case, the bubbles are flat because they're pressing against sea ice, which is still there on the surface. And so the bubbles can't easily escape into the atmosphere. When the ice has melted, the bubbles go up into the atmosphere. And here we see a picture taken from a submarine showing the methane bubbles rising up to the surface. Well, we've now come to the end of the first half of this presentation, where we've talked about the warming of the planet, what's causing that warming, which is greenhouse gases, especially carbon dioxide and methane, and what one of the sources of methane is, which is the seabed of the Arctic, where huge amounts of methane are contained in the sediments, and as the seabed thaws out or melts because the water's getting warmer, that methane comes out into the atmosphere. There are many other sources of methane, which I'll talk about in the second half, and the main thing we're going to look at then is, can we find ways to actually get rid of these gases so that the carbon dioxide and methane content go down back to the level before the Industrial Revolution, so that the temperature of the planet should go back to the level that it was then. So instead of having really extreme heating, which is causing real danger to the survival of the human race, we might be able to go back to a climate which was more livable, the climate we had in the past, and the quite recent past, just early this century. So that's what I'm going to deal with next. Now we say a little bit more about this Arctic methane, which is a real threat to the continued existence of the human race. Given that there's a possibility that all of the methane from the Arctic will come out in a very short time because of melting of the sediments, what would happen? And well, I did some work with a computer model with colleagues, and we just modeled what would happen if 50 gigatons, that's 50 billion tons of methane, came out of the seabed in one go. That's only about 8% of the methane that's there. So it's the real disaster, the actual disaster that would happen could well be much worse than this. But if you assume just 50 gigatons and then model what that would do to the temperature of the planet, this is what we get. The blue, this is a family of curves which represent warming of the planet with different sort of assumptions about how good we are at taking greenhouse gases out of the atmosphere. So let's consider the blue, the middle blue here. This is the way the planet would warm up if we made some attempt to take carbon dioxide out of the atmosphere, but not a good attempt. This is quite likely to be what happens. But if you have this methane outbreak, it warms everything up. And here we have the red curve instead, is what happens to the planet with this methane outbreak. Now, in our model, the rise was only 0.6 of a degree. Now that's, given that the temperature rise has only been 1.2 degrees since the Industrial Revolution, we're getting a rise of half as much just immediately from the seabed methane melt. And even worse, our results were repeated. The work was repeated by an American scientist last year, and she got an even larger rise. She got a rise of 1.2 degrees using more recent modelling techniques. So the rise of temperature could mean that we're doubling the amount of warming from the Industrial Revolution simply due to Arctic methane coming out of the seabed, which is really a frightening prospect. Now, what would that cost? One of my colleagues is an economist and worked out what that would cost, and it would be something like $60 trillion in 100 years. That's the cost to the world of having all this extra global warming. $60 trillion sounds a lot, but it's only about 15% of the amount of cost that the world is incurring from emission of carbon dioxide anyway, but it's a lot. Now, methane is a cause of concern because of this thing I showed where the level of methane in the atmosphere seemed to be flattening off and reaching some standard level for some reason we didn't understand. But then it started to take off again, and now it's going up very fast. And we need to try to understand why that is. So what are the things that are causing methane to increase? We know what causes carbon dioxide to increase. It's burning coal, burning oil, driving your car around with petrol. Anything that burns fossil fuel, oil or coal, releases carbon dioxide, and that's causing the carbon dioxide rise and the global warming rise. That's simple, but methane is coming up fast, the amount of methane in the atmosphere, and it has a variety of sources. There isn't one simple source, just lots of them. And some of them are due to man and some of them are due to nature alone. So these are some of the ones that are due to man. First of all, we produce far more waste than we used to when we had a lower population, and the waste is put in great piles, waste heaps, and decomposes, and as it decomposes, it releases methane. So that's waste sites. There's still methane released from fossil fuels. That's especially gas. Natural gas is one of the main sources of heat and fuel for Europe. Natural gas coming from Russia, and that natural gas leaks as it's transported through pipelines and through various systems to burn it. It leaks, and the methane loss from leakage is large. Rice cultivation, a surprise. You think, well, there's nothing more ecologically viable than growing rice because it's the staple food in Southeast Asia. But the trouble is, you grow rice in rice paddies where it's flooded, and that flooding causes the rice leaves of the rice to rot, and that produces methane. So there's a source of methane, which is rice cultivation. And again, with the population rising everywhere, the amount of rice that people are eating is increasing. So the rice methane source is getting bigger. Domestic ruminants, these are the worst of all, and only recently have people begun to realise just what a bad effect cattle and pigs have on the world, especially cattle. The number of cattle in the world has increased really fast because in poor countries like China, people couldn't afford to eat meat, but now they can, and because they can, they do. And all of the poor countries of Southeast Asia, where meat consumption was low, the meat consumption has now become high, and that means more cattle. And cattle produce methane, enormously large amounts of methane, from the fact that the the grass that they eat, they have to chew and redigest. And as they do that, and it rots inside their stomachs, it produces methane. So cows are big sources of methane, really serious sources, and that's quite a large chunk of the world's methane production comes from cows. And this is burning of biomass and fuels. So we see there's a variety of sources, and it's going to be hard to get rid of any of them. For instance, we can be more careful about getting rid of waste. We can't do much about rice cultivation. Cows, the hope is that you can feed cows with something different. Apparently seaweed is very good. If you feed a cow with seaweed, it doesn't produce as much gas. So we can shrink the methane, but it's difficult to do so because there are so many sources. Now, these are the natural sources, and the biggest natural source here are wetlands. That is marshes, water, rivers. It's where there's land which is wet and where the contents rot away. And whenever vegetation rots, it produces methane. So the biggest source are wetlands. But we see an increasing slice here coming from permafrost, because permafrost is the permanently frozen ground that you get in the Arctic. Now, the trouble is, permanently frozen isn't permanent anymore because of global warming. So a lot of the permafrost in the Arctic is melting and turning into water, but the water has got vegetation in it, rotting vegetation from the distant past, and that continues to rot and produce methane. So permafrost as a source of methane is going to become bigger and bigger source. Then there's some other ones here. Termites generate methane when they're busy as termites. Fires generate methane, and wild animals do the same thing as cows, and fresh water is a source of methane. So there's a lot of natural sources, but the biggest natural source is wetland. So permafrost, while we're talking about permafrost, we should worry about it because permafrost is found under about half of Asian continent, most of Russia and some of China. And it's warming up because the climate's warming. These are some measurements made at a place in northern Alaska called Dead Horse, which is a very small town, has a population of 1. And I've been there. And every day, this one person measures the temperature of the permafrost at Dead Horse, and it's been rising, as we can see, quite rapidly. And everywhere you look, permafrost is warming up, and in some places is thawing out, turning into water with rotting vegetation, which will produce more methane. So methane in the future is going to be coming from the loss of permafrost. It's been called the ticking Arctic time bomb because it will take several decades for it all to disappear. So we've talked about sea level rise as one consequence of climate warming from the melting of the Greenland and Antarctic ice cap. We've talked about this potential huge methane release from the Arctic seafloor, which could be a real shock to the planet. So then the third thing I'm going to talk about is the jet stream and extreme weather events. Now this is another very serious problem which has occurred and which again has just been recognised. Now in the past, the left-hand picture here shows that there used to be a very steady, very strong wind that blows from west to east at some middle latitude of the northern hemisphere. That's the blue arrows. North of it, right under the pole, you have very cold air, polar air, and this is called the polar air mass. And then further south, near the tropics and the equator, you have a warm air mass, the tropical air mass. So you have tropical air mass in low latitudes, a polar air mass under the poles, and dividing those two, you had a very strong eastward flowing wind called the jet stream. And you would know about this if you fly between America and Europe, because it makes you get from America to Europe more quickly than you get from Europe to America, because the wind is blowing eastward. So that's the way it was, and it was a very strong, very steady wind. Now what's happening now is that wind has slowed down. And the reason it's slowed down is that it's driven by the temperature difference between the Arctic air and the tropical air. And that temperature difference is decreasing because, as we showed, the Arctic is warming 3 times as fast as lower latitudes. So that dark blue cap on the planet of cold air, that cold air is warming up, and it's warming faster than the warm air in the tropics. The temperature difference between the polar and the tropical air mass is decreasing. And that decreasing temperature difference doesn't drive the jet stream as rapidly. So the jet stream is slowing down. And when it slows down, it stops being a steady, strong eastward wind and starts to become a wind that's broken up into little eddies or big eddies. And we see something like we see on the right-hand side, where instead of a straight line marking the wind is broken up and into eddies. And this means that in some places we find the warm air from the tropics can move further north than it should do because of a lobe of this jet stream that's tilted this way. And in some places, the very cold air from the polar regions can move further south than it ought to. So we have cold air occurring in places where it's normally warm, and warm air occurring in places where it's normally cold. So what you experience when you're on the Earth's surface is a sudden, extremely cold outbreak, something colder than you've ever known, or an extremely hot outbreak, hotter than you've ever known. So all the heat records are broken by these warm polar air moving north, warm tropical air moving north, and cold records are broken by the polar air moving south. Now, here we see a simulation of this by NASA, and here's the jet stream. And here we see it's taken up a shape where hot air from the Midwest, the midwestern states of the US, has moved further north than it should be. So you're getting hot air over the Canadian prairies. And over here, the cold air that should lie over the pole is moving further south and has got down to here, which is the eastern part of the United States. So the eastern part of the United States that's normally quite warm can become suddenly very cold, and the Midwest of Canada, which is normally cold, can become suddenly warm. These are the kinds of things that can now happen, and they're called extreme weather events. They're not climate, they're weather. So what happens? Well, I won't show you pictures of all the terrible floods and hurricanes that have happened, but you you've seen those on the news. But what I can show you is what it's done to crops. Now, the brown colour here is the intensity in which we grow crops for food. And we can see that the food crops of the world are grown most intensely in the Midwest of Canada and the prairies, in Europe, in Ukraine, and in Western Russia. There's also India and China, but let's look at these places. These are the places where the jet stream has started to break up. So instead of reliable eastward flowing winds over these parts of the world, you're getting the jet stream breaking up into eddies and giving us unreliable weather. So when we need reliable weather for growing our crops, we're not getting it anymore over this very wide swath of North America, Europe and Russia. And that's a real worry, because we know that most of the crops that people eat have reduced yields if the temperature gets very high. Now, these are the 5 main food crops grown on the planet, and that's maize, soybean, rice, wheat, and another type of maize. Now, in each case, if you warm the climate, this is the climate, the temperature as it was in pre-industrial times, as you warm the climate for a little while till the temperature's risen about 1.5 degrees, the yield of the crop increases. You're getting, if you warm the climate, you get more growth. But then when the temperature gets higher still, up to 2 degrees or more, the yield of the crop starts to go down very rapidly, and that's because it's withering away. It's drying up in the hotter climate, withering away, and you're getting less of your crop. So this is one of the main reasons why in the Paris Climate Agreement, the world agreed to try and keep global warming to less than 1.5 degrees. It's to keep it below a temperature at which crops have lower yield, and so we have less to eat. And we can see that we're getting up to that temperature now. And because of these weather extreme events, we've lost crops due to these sudden warmings and sudden coolings. And the extent to which this happens was calculated by the United Nations. The United Nations Climate Programme designed a measurement which is the average price of food everywhere in the world. So you measure the price of food everywhere, rich countries, poor countries, and take an average, and it's called the Food Price Index, and they started this in the year 2000 at 100, and then measured how the average food price has changed since the year 2000. And this is what they found. The food price increased very rapidly until 2009, when it was 220, which means that the average price of food throughout the world in the year 2009 was more than double the average price of food in the year 2000. Now, that's due to lots of factors, of course, one of them the increasing population of the planet. But one of the factors is the fact that we've been having increasing amounts of extreme weather in this region affected by the jet stream. And this has been bringing on extreme heat and extreme cold, and that's causing a loss of crops. Now, that's an inconvenience for countries like Italy and Europe, but in poor countries it's a disaster. If you look at poor countries in the Middle East, for instance, where you have most people or many people living in cities, very poor, not able to grow their own food because the city doesn't have any farmland, and having to buy food, but finding it increasingly difficult to buy food when the crop yield has gone down. So these little arrows and place names here are parts of the world where the price of food went very high, and the result was civil unrest, revolutions, warfare, because people didn't want to just starve, they would revolt. So places where revolts happened, it seems to correspond to times when the food price is very high. A whole collection of unrest here in 2009. Then the food price went down and then came up again in 2011, and again we had another collection of civil unrest. So this can only get worse. The population of the world is rising, and the climate is getting more and more uncertain because of the breakup of the jet stream. And the uncertain climate is producing high food prices, and therefore difficulty in buying food if you're living in a poor country. Now, the effect is going to be greatest in Africa. The UN did an analysis of what we can expect the population of different parts of the world to be by the end of this century. And we see most regions have an increase in population. Europe has a decrease, but most of the other regions of the world have an increase. But the increase is 20 to 30%, which is going to make it difficult to feed the world, certainly, but not impossible. But Africa, the prediction is the population will quadruple by the end of this century. And this is a truly frightening prospect, to have 4 times as many people in Africa. Because firstly, Africa can't feed itself now. It has to import food, especially food aid from the United States and Europe. Africa needs aid to provide enough food for people to eat. And now we're talking about 4 times as many people. So there'll be a massive effort by people to migrate out of Africa and come to Europe. We're already seeing that. But what looks like an increasing flow of migrants now is nothing compared to what will happen by the end of this century, when we'll have an increase from 1,100 million people to 4,380 million people. And we set alarm, because how are we going to feed that many people? We can't feed this many people. So to feed 4 times as many people, it's really difficult to see how it can be done, unless Africa adopts contraception or adopts methods of reducing its population growth, which it isn't doing. And the result I can see is going to be a catastrophic disaster. So I'm afraid this is something that the statistics show the world is going to be suffering from. Let's look at other effects. All effects, I'm afraid, are bad. The next one is things happening to the ocean. Now, when you add more carbon dioxide to the atmosphere, some of that carbon dioxide dissolves in the ocean. And when you dissolve carbon dioxide in water, you get carbonic acid. Now, carbonic acid is an acid, so having an ocean with a higher level of carbon dioxide above it is going to mean that there's more dissolved carbon dioxide in the ocean, and the ocean will become more acidic. Now, the measurement of acidity is a function called pH, and the ocean pH has been going down, which means the acidity of the ocean has been going up, and this is measured in Hawaii. But if we look instead at acidity, here it is going up, and this is the ocean acidification has been going on since 1880 because ocean measurements have been done since then, and it's accelerated in recent years, since 1960, and this is because an acceleration in the amount of carbon dioxide in the atmosphere is giving you more acidity in the ocean. Now that has a bad effect because as the ocean gets more acidic, it means that creatures in the ocean that depend on low carbon dioxide levels die off. And one of that is shellfish, because shellfish of all kinds have shells which are made of calcium carbonate, that's chalk, and as the ocean gets more acidic, the acid dissolves the calcium carbonate. You know from school chemistry that when you add chalk to acid, the chalk dissolves and bubbles away. It's the shells of marine animals, everything from tiny animals right up to quite big shellfish. All of those shells are starting to dissolve because of the extra amount of carbon dioxide in the water as carbonate. So this acidity of the ocean has been rising. We see that it's rising in an accelerated way, and this is going to result in the loss of a lot of the marine life, because shellfish and also the little tiny shellfish called foraminifera, the minute shells, these normally sink to the seabed and we get rid of them. But if they dissolve back into the ocean, then that's adding to the amount of carbon dioxide in the water, and that again is increasing global warming. So we see an effect of killing off marine life and increasing global warming both at the same time because of the dissolving of carbon dioxide in the ocean. So another bad thing, everything that's happening as a result of global warming seems to be bad. There isn't any good thing. So that means we have to think, what can we do to try to offset all these bad things that are going on? Well, firstly, we want to offset the warming of the planet. Well, one way is to reduce carbon emissions, but the trouble is, if you reduce emissions, it doesn't actually cool the planet down. And the reason is that carbon dioxide stays in the atmosphere for a long time. One of the bad things about carbon dioxide emissions is that it stays, when you emit some from burning fossil fuels, it doesn't go away, it stays in the atmosphere for hundreds of years. So all the carbon dioxide that we have in the atmosphere now is carbon dioxide that some of it was put in the atmosphere 100 or 200 years ago by somebody burning coal, burning a stock coal in a steamship in 1900. That carbon dioxide is still in the air today. So carbon dioxide you can't get rid of it by reducing your emissions. And this is a gigantic mistake which the world is making at the moment, and a lot of climate scientists are making that, is that they think that all we have to do is to reduce our carbon emissions, switch to away from fossil fuels, switch to electric batteries, do away with burning fossil fuels and we'll be okay. But all that will happen is that the world will warm up more slowly from the remaining carbon emissions. It won't actually get cooler because there's less carbon dioxide in the atmosphere. There's always going to be more. So we need to do much more than just reduce our emissions. And unfortunately, the Intergovernmental Panel on Climate Change has only focused on reducing our emissions and not on removing carbon dioxide. So the only real solution is taking the carbon dioxide out of the atmosphere. So the Paris Agreement, by which everybody agreed to reduce their emissions, is false. It won't deliver a cooler climate. It will only deliver a warmer climate, which is warming more slowly. We've got to get the temperature down, and the only way to do that is actually take carbon dioxide out of the atmosphere. And this is a process called direct air capture. And most scientists see that, but not all, and certainly politicians don't see it. So the politicians just talk about reducing our emissions. And you'll hear a lot about carbon emissions being reduced, but be suspicious, because it's not reducing emissions that cools the climate, it's taking carbon dioxide out of the atmosphere completely, and that's much more difficult. But I'll show some of the ways we can do it. Firstly, this is the danger. If we look at, this is the amount of different forms of energy that we use. And we can see that we're still using a lot of fossil fuels. The black, red and blue are coal, oil and gas. And we can see these are still the major sources of energy for the world. The small columns in the right are nuclear, wind and solar and hydropower. These are the ones we're trying to adopt to replace fossil fuels, wind and solar especially. But we haven't been very successful up to now, because you can see how fossil fuels still dominate. So we do have to reduce our emissions of carbon due to fossil fuel burning, but it's only a start. We need to do more than that. So this is the dilemma. This is what climate warming is going to be doing over time. If we don't do anything, the warming will accelerate. This is the red, and it's what scientists call business as usual. That's not doing anything but letting things go. If we cut our emissions aggressively, reduce our carbon dioxide that we emit, we can reduce the rate of warming of the climate, but we can't reduce it to below zero. We can't cool the climate. So the best we can do is reduce the warming rate to a lower rate of warming. We have to remove carbon dioxide, that's the green arrow, to actually bring the temperature down. There's another way, which I'll talk about, which is called radiation management, which can also help. But mainly it's taking carbon dioxide out of the atmosphere, can get us down in terms of cooling, while reducing our emissions can't. Now, the first way is this one called Srm, Radiation Management. And this is something that we can try and is being developed by a lot of groups. And I've been involved with some of that work. And it seems to me to be a great method. It's called marine cloud brightening. And what happens is that you want to release water vapor or water particles into clouds, and they then cause the clouds to become brighter. And a brighter cloud reflects more energy back into space, and that cools the climate. So here we see what water vapor does to clouds. It looks like it's looking like vapor trails from a plane looking down at the sea. This is the Bay of Biscay. In fact, you're looking up at the air, and this is where planes are flying overhead, and you're looking at, or actually ships are sailing down below, and you're looking at the water vapor produced by the ship's funnels. And here we see this pattern of water vapor. So the idea that was had by a Scottish scientist called Salter is that you build a ship. This is a kind of an unmanned ship, a drone ship, and you pump water up these masts with a very fine nozzle at the top to divide it up into very finely divided particles, and you release those into clouds, into low-lying clouds, especially the sort of clouds you get at sea, marine stratus clouds. The vessel is unmanned, but it's controlled by a computer, and the propulsion is these masts which actually revolve, and that gives you some propulsion. They're called Flettner rotors. So here's the design, and he reckons we need about 200 of these all over the world's oceans to produce enough vapor to cool, to brighten the clouds and increase the reflection of radiation from the Earth. So this describes what it is. We're increasing the droplet concentration in these low-lying clouds called stratocumulus, and the effect of making clouds brighter and therefore emit more radiation is called the Toomey effect, and that was only discovered in 1990, quite a recent piece of basic physics. So you put these droplets into the cloud. So here we see the cloud with these droplets in, emitting radiation into space, and if you have the smaller the droplets you have, the higher the albedo, and therefore that's the more radiation is sent out into space. And we know that because if you look at a thundercloud, it's dark. When it's about to rain heavily, you see dark black clouds, whereas the clouds you see in fine weather are bright and fluffy. And that's because the bright clouds in fine weather have tiny water particles in them, which make the cloud bright, and it puts a lot of this brightness back out into space. The big dark clouds reflect less radiation into space, and that warms up the planet. So cooling the planet can be done by making clouds brighter. This is a wonderful thing which seems to work. So you can see this, how the size of the particles matters. If we look at glass beads ground up, here we have glass beads in this bottle ground up into 40 millimeter diameters, and it's quite dark. But if you grind it up further into 40 micron diameter, it becomes bright. So you imagine a cloud made up of these beads is going to be brighter and will reflect more radiation into space than a cloud made up of these big beads or big thunderclouds. So that's the Toomey effect. And so his design of Salter, we showed you before this design. He's come up with another design where you spray the water. Instead of spraying it vertically, you spray it horizontally. So just a new design. Well, that's one way, and that I think it would work. But let's look at what so far the world has only agreed on, which is the Paris Agreement of 2015. Now, the Paris Agreement says we need to try to keep warming to less than 2 degrees. That's because of the effect on crops, and even to try and keep it to 1.5 degrees. We should reduce our greenhouse gas emissions as quickly as we can. And each nation should say how fast it's going to go. Some nations haven't said that and aren't really doing very much, but every nation should be working together. But we see the weakness in the Paris Agreement is it only talks about emissions. It doesn't talk about carbon dioxide removal. And this, people are realizing this makes it a weak agreement. So let's look at the other ways, as well as marine cloud brightening, that we can get rid of carbon dioxide. Well, one way, these are 3 methods that have been proposed, and I don't think any of them are going to work except direct air capture. Firstly, afforestation means planting millions of trees. Now, trees are good. They take out carbon dioxide from the atmosphere and put in oxygen, but they're not that good. That is, if we consider the carbon dioxide put into the atmosphere in the whole of Europe and how many trees you'd have to plant to remove that, it turns out that the area of trees you'd have to plant in Europe is 6.4 million square kilometres. Now, the trouble is that is the area of Europe. So we'd have to cover the whole of Europe with trees in order to offset the carbon dioxide produced from our factories and cars. Well, obviously we can't do that. Another method is to burn crops, collect up the carbon dioxide and store it. Well, that's not a great method either. That's going to use up 2.5 million square kilometres. And the final method that's been suggested is you take certain rocks, olivine rocks, that's limestone, you grind them up into powder, you spread them around the world, spread them on beaches and parks and roads, and they slowly absorb carbon dioxide. But it's very slow, and then when you've absorbed the carbon dioxide, you have to go and grind up some more rock. So it's not a great idea. So the only one that we think will work very well is air capture, where we take the carbon dioxide out of the atmosphere and let it put it somewhere. Well, one way to do this, but it's again not very powerful, is to produce a substance called biochar. And what that does is to take agricultural waste and to distill it in a kind of big boiler, and it produces a substance like charcoal and an oil, and it absorbs carbon dioxide. So it does take carbon dioxide out of the atmosphere. And the Amazon Indians used to produce biochar in order to be able to make their jungle less wet and better able to make food from it. This is some experiments in America where, in fact, biochar is being produced from the waste of pistachio nuts, which are being grown in an agricultural area of Ventura. And here, the digester, the plant that produces the biochar, is attached to the university's normal diesel generating plant to produce a decrease in the amount of carbon dioxide. So here it is, and here's one of the digesters. You have lots and lots of these that you drag through the fields, and you put pistachio nutshells into them, and you get this oil and biochar. So the nuts are actually, you're taking the carbon dioxide or taking the carbon out of these nutshells. So it seems stupid, but it works. And you need a lot of nuts, obviously, so you only do this in an agricultural district. That's the one solution. The biggest solution is actually take the carbon dioxide out of the atmosphere. And that's a huge job. And I don't know if we're going to be able to do it, but we put, at the moment, 42 gigatons of carbon dioxide into the atmosphere per year. That's gigantic, 42 billion tons. 1 gigaton is 1 billion tons. So if we want to cool the climate, we've got to take more carbon dioxide out than we put in. That means we have to take out more than 42 gigatons of carbon dioxide per year. How do we do that? Well, there are methods that have been put into effect, but on a small scale. One is a company in California where you take the carbon dioxide out of the air by absorbing it into a liquid which absorbs CO2, but then you react the carbon dioxide with lime, calcium oxide, to produce artificial limestone. And here is the artificial limestone being produced. And it's a way of doing something, here it is again, and this is a way of doing something with the carbon dioxide that you've taken out of the air. And so the way, here's the technician is showing us how the nodules of limestone that you've taken out of the air, you put into cement, and you produce a form of concrete in which you reduce the carbon dioxide content of the concrete by injecting it with this limestone. So this works, and in fact it's been demonstrated that the concrete that you produce from the carbon dioxide in the air is actually capable of doing all the jobs that normal concrete does, but you don't produce a lot of carbon dioxide from the manufacture of that concrete. And the demonstrator here was an airport terminal at San Francisco Airport, where they re-roofed the terminal with concrete made from carbon dioxide in the atmosphere, and there was a net reduction of carbon dioxide from the atmosphere by this process. That's an amazing thing, that we can reduce CO2, even if we use the CO2 to produce concrete, which is normally a method which actually adds more CO2. So there's a lot of promise in that method, made by a company called Blue Planet. But there's also the simpler method of just pumping the carbon dioxide you've taken out of the air down underground. And the company that does that in Europe is called Climeworks, and its biggest plant is in Iceland. There's a plant to take carbon dioxide out of the air. You then pump the carbon dioxide down into big caverns underground, which exist because of the volcanic nature of Iceland. So the Icelandic volcanic cavities are the place you can put the CO2. The energy comes from the earth, from the warm production of the volcanoes. So this company is called Climeworks, and there was an experimental branch of this. The only one in Europe was run by Polytechnic of Turin, and it was situated in southern Italy, in Puglia. And so this is trying to do the same thing, take carbon dioxide out of the atmosphere and bury it, and using solar energy or wind energy to do it. So, and that again is in association with Climeworks. So the Polytechnic here in Turin is a leader in Europe in carbon dioxide removal, and it's unfortunately temporarily closed down that works because of COVID. So we can convert it into limestone. There's also ways you can convert it into jet fuel. Again, the trouble there is that when you've got the jet fuel, you burn it and that produces carbon dioxide again. So we haven't really gained. This just shows the sequence of events where you blow air over a liquid which absorbs the carbon dioxide, and then you have to clean it, dry it, and pump it underground, or react it with something else to give you the limestone. So that's the principle. This is an experiment in Canada where you're blowing it over the absorber. That's all these blowers here, and turning it into jet fuel, which of course it doesn't use carbon. It doesn't use up any carbon dioxide, or doesn't produce any, but it's neutral. It doesn't get rid of any either. This is the plant in British Columbia. So here we have the methods that have been used, but only experimentally. What's needed, if this is going to remove 42 gigatons per year out of the atmosphere, then we can't just have a few experimental plants like this. We need a global effort, a gigantic global effort, to build thousands of these plants for removing CO2. And the question is, because the planet seems to be focusing on simply reducing emissions, which is a mistake, then we're never going to get the climate cooled down if we don't actually take CO2 out of the atmosphere. So that's what we have to be, the challenge that's facing the world, and the world isn't yet facing up to it. Anyway, I'll end up with a few, again, recent pictures. This is, again, the Greenland ice cap, which we went back to this year, and it was even darker than it was previous year. And this is where you see the black ice, which is because the amount of dirt has collected on the ice, and the ice itself has turned into water, so that what remains gets blacker and blacker, and that absorbs more and more radiation and gives us a more rapidly melting Greenland ice cap. So here the water's run off, but it hasn't run down to the bottom, it's collected in a kind of pool. That's this year. And just to show you something that's being done that I'm in touch with, and you may want, I'm part of it, and you may want to look at it as well. It's to encourage the use of electric cars instead of, the world shouldn't be, one way to reduce carbon emissions is to have electric cars which are driven by renewable energy, solar or wind energy, to generate the electricity which drives the car. So you have a battery. And of course the world is changing towards electric cars, but the method to try and encourage it was to have races using electric cars in remote places. So here's an electric car for a race on the Greenland ice cap. And in fact, this explains why I was on the Greenland ice cap. The company is called Extreme E, and you will be able to see the races if you go 5 times a year. They have races in remote places, and you can watch them. So this was the race that was done in Greenland last year. These are the drivers, and these are drivers helping the science by collecting ice and dirt samples from the ice cap. So the drivers were very helpful here, and this is one of the drivers you may recognise who has switched to racing electric cars. That's Jensen Button, who's a very famous Grand Prix driver, but he's now racing electric cars, and here he is posed in front of the Greenland ice cap. And this is another driver who, they have men and women drivers, and she's been a champion. And here we see where one of the other drivers pointing out where the water is melting off the ice cap and running down towards the sea. And here we see a sort of waterfall from the meltwater. So I'll just end with this rather frightening picture I talked about the threat to the climate due to cows. And in fact, this threat is much worse than people imagined. Most of the weight of biomass, that's the weight of people and things on this planet, is cows. Livestock make up 60% of the weight of mammals on planet Earth. Humans make up 36%, and wild animals, the ones you see about when you watch an Attenborough program, is only 4%. So nearly all or most of the weight of living creatures on this planet are cows, and cows produce methane. So we've got to try to reduce the amount of food, the amount of animal products that we eat, and try to eat more vegetable products. If only, apart from cruelty, it's if only because that will reduce the number of cows, and that will reduce the amount of methane they produce. And that will save the world, and it will save the wild animals as well that are dying out at a very rapid rate, like polar bears. And so I'll just show you some things you might want to look at. Obviously, Greta Thunberg has been raising the alarm, and everything she says is true. So the 2 things which I think you really would benefit from reading or seeing is this book describes all the things I've talked about today, and it's called Addio ai ghiacci, and I'm the author, and it's translated by my wife. And then a film, a full-length film produced by Leonardo DiCaprio, and it's all about these effects, including the methane, and the picture here shows a person who's been set on fire by putting his stick through a hole in sea ice into the methane-laden water. And it deals a lot with how we try to reduce carbon dioxide in the atmosphere, the thing I was talking about towards the end. So I recommend you try to see that film. You have to see a pirated version because they're not willing to, the producers don't like to show it. This is what will happen to us quickly if we're not careful. This is the Greenland ice sheet showing the thickness of the ice sheet on top of the continent. Now, Greenland is an island which has a kind of bowl shape, and in the middle it's below sea level. But because of the hugely thick ice sheet, 3,000 meters, Greenland is a mountain. It looks like a great bulging mountain. But if the ice sheet melts, all of that ice will go. That will raise sea level by about 7 meters, and we'll have a bowl in the middle. So those are some of the dire things that are happening. So what I'm saying really in all of this is that greenhouse warming is accelerating. it's not just warming the temperature, warming the air, it's changing sea level, it's changing it's affecting the presence of life in the ocean. It's increasing the amount of methane in the air. It's doing a lot of nasty things. It's producing these random extreme weather events. So we're not just getting a warming from our CO2, we're getting a lot of other bad effects on the planet. So we have got to reduce the CO2 from the atmosphere using the techniques I've talked about here. It's not good enough just to reduce emissions. We have to get rid of CO2. So I think we need high technology here and high engineering skill. So I'm sure that exists in Polito, and I look forward to you, some of you in the future, being involved in this work and helping to save the world from climate warming.